everyone, I am Gengyuan, and it's my pleasure to present a paper titled Can Vision Language Models Be a Good Guesser? Exploring Vision Language Models for Times and Location Reasoning at WCV 2024 in Hawaii. We're researchers from Germany. So first, let's take a look at this photo on the slide. Can you tell where and when this picture was taken? The scene is rich with cultural cues, beer barrels, people dressed in the traditional barbarian costumes, and the festive atmosphere, obviously. So these visual elements might suggest that this image was captured in Munich, Germany, possibly during the well-known celebration of Oktoberfest. And this process of reasoning and deduction is something we as humans often take for granted. We combine our visual perception with our cultural knowledge and past experiences to make an educated guess about the times and location of image shooting. But what about the machines? This brings us to the core question of our research. Can vision language models reason about times and locations by interpreting visual cues as we humans do? In this work, we will explore the vision language models, process the visual data, and to which extent they can mimic human-like reason. So in conclusion, our work introduces a two-stage probing approach. We call it recognition and reasoning. So this two-step probing approach is designed to assess the vision language model's capacities in two distinct but interconnected tasks. So in the first stage, recognition, we challenge the discriminative vision language models to identify times and locations depicted in the image. This is formulated as a multi-class classification task to classify the times and the location of a given image. In the second stage, reasoning, we evaluate generative vision language models, which must do more than recognition. So it must explain and question answering task. For the same image, for example, a generative vision language model would need to provide an answer and also the rationale, such as in this photo, the vision language model must tell this photo is taken in Germany because the people on this photo were wearing traditional Bavarian clothes and celebrating with beers and barrels, which possibly on Oktoberfest. This reasoning mimics a more human-like approach to problem solving. And also, to facilitate the research, we have constructed a new dataset we call Wikitail, which dubbed as Wikicon Times and Location. This dataset is carefully curated to include images captured over a really broad time range, ensuring the temporal diversity. Additionally, we've aimed for geographic balance to mitigate cultural bias, thus enabling a more rigorous and fair assessment of the vision language model's reasoning capacities. So in our Wikitail dataset, it consists of more than 6,000 images, each annotated or curated with specific times in year and country where the image was taken. Our dataset encompasses an impressive historical range from the year 1826 to 2021, providing a rich temporal cross-section for analysis. And with Wikitail, we cover 3 countries across 4 continents: Europe, Asia, America, and Africa. This geographic diversity allows the vision language models to encounter and learn from a variety of cultural and environmental settings. Moreover, we've taken an innovative approach to consider regions with a high level of geological concept, transcending traditional country borders. We recognize that cultural borders often do not align with political ones, and our dataset reflects this complexity. As you can see from the image displayed on the slide, from Mexico in 1890 to China in 2010, our dataset spans a vast area of cultural moments and locations. This dataset is a fundamental element of our research, and we believe it will greatly contribute to the field, providing a level of depth and breadth of training and evaluating vision language models for times and location reasoning. In this section, we detail our probing approach, which is divided into 2 stages, recognition and reasoning, both essential for assessing the capacities of vision language models. First, the recognition stage, the vision language models are tasked with identifying visual features from an image to generate an answer. This is a straightforward task where the model uses discriminative methods to recognize and classify visual features. And next, we have the reasoning stage. This goes a step beyond recognition. The model now takes the context, the questions and instructions into consideration and integrating with visual features to produce a contextually conditioned answer based on the large language models. The key distinction here is the methodology. So discriminative vision language models they rely on text agnostic visual encoders and vision-agnostic texture encoders, focusing purely on the visual part. In contrast, generative language models leverage the large language models that process visual features in the light of context provided by the questions and instructions. For the recognition stage, we use two different settings, the zero-shot setting and the linear probing setting. So the first one, the probability of an answer is the exponential of the similarity between the visual features and text embeddings. This assesses the model's ability to classify the images without prior specific training in the dataset. And next, we use a linear prober where a simple linear layer is trained on the top of the visual features to predict the answer. This evaluates the model's capacity to learn from the dataset with minimal parameter updates. For the reasoning stage, we introduce a model prediction probability of the answers conditioned on the both visual features and also the provided context in text. So together, these formulations provide a comprehensive framework to probe the depth and the flexibility of vision language models and understanding the visual and contextual data for time and location reasoning. So this table presents summaries the accuracy, precision, and F1 score for each model to tell the shooting times, country, and region of an image. We also evaluate 3 different models, clip, bleep, and VLMs in recognition stage, and 2 different language models, enhanced vision language models, Open Flamingo and Llama Adapter. We also report the frequency baseline and the human baselines. And we also conduct a linear probing on 3 different visual encoders above, and also on a pure vision encoder, which is ResNet 50 trained on ImageNet on times and region classification task. We also find that most models, including clip and bleep, have a performance improvement, which shows actually both of these vision encoders, clip and bleep, can already catch the relevant features for times and location reasoning. So firstly, we found that clip-based models stand out, achieving the best overall performance in all the categories. This is a testament to the robustness of their training and architecture of clip. And we also see that larger models like clip large demonstrate superior performance compared to their smaller counterparts. This suggests when it comes to vision language models, size and the scale of the model correlate with the ability for reasoning and for recognition. And after implementing linear probing, both clip and bleep encoders exhibit a good performance. This improvement post-probing indicates that these models have effectively learned visual features for the recognition of times and location reasoning. And we also visualize the work patch alignment between the different models. We found that actually the model can catch important areas like the text and the human clues that are relevant to identifying the times and locations already. And for the reasoning stage, there is a notable performance gap between the discriminative and generative vision language models. Looking at the in-context learning models like Open Flamingo, we find the performance is marginally just better than the frequency baselines. This just suggests that while these models can learn an output space of the labels, their learning is limited when it comes to applying the contextual understanding. More strictly, even with the integration of large language models, of generative models fall short of reaching human baseline performances. This indicates a significant room for improvement in how these models process and generate language based on visual input. We also postulate that this performance discrepancy stems from 2 core challenges. First, the context-conditioned visual features in counter models may not retain enough answer-relevant information. And second, even large language models seem to struggle with reasoning solely from the visual cues. In summary, our findings of this paper reveals that, first, discriminative vision language models performed already pretty well in recognition tasks, showing that they can effectively extract visual features without any context. And second, generative vision language models fall short of human baselines, indicating that large language vision language models have yet to fully leverage their extensive knowledge for reasoning the times and location. And also, we suggest that the performance gap between the generative and discriminative vision language models may be due to 2 factors. First, the inadequacy of context-conditioned vision features to retain the crucial information. And secondly, the limitations of large language models in reasoning with visual cues alone. We hope this insight can improve the understanding ability of vision language models for times and location reasoning. Thanks for your attention.